Okay, so I'm gonna finish up the chapter. Actually, this should be 1C because I broke up the previous lecture into two pieces. So we're gonna cover this section 1.4 on Thevenin's theorem. Um, there is a section 1.5 where there's a lot of matrix algebra. Um, for, for this class, since linear algebra is not a prerequisite, I'm just going to describe things conceptually and why that's useful. But then we're not going to have any pre-lab or homework on it. So watch that, and hopefully it gets you the concept of why these matrix solutions to circuits are useful, but it's not necessary for our class coverage because we tend to simplify the circuit down quite a bit anyway. And when you're trying to solve a general circuit, it's actually useful. But the thing we actually want to really get you guys to understand now is simplifying circuit. So we already done this thing where we have resistors in series, right? We can have an equivalent resistance, resistance in parallel. We can have an equivalent resistance. And now this is actually Thevenin's theorem actually covers any components, not just resistors. And it basically just kind of shrinks your circuits down into, even if it has started off with like 1,000 components, it just makes up some number, right? You can make that equivalent to basically a Thevenin's voltage and a Thevenin's resistance. And I'm going to be careful when I start mixing up the word impedance and resistance, but for now, let's just think about this in terms of resistance. So the idea is that anything, like let's say I have this crazy circuit that has, multiple resistance, multiple battery power supply. Let's say this is connected to ground, right? And then you have another resistor here. Maybe you have another resistor here. You have another resistor here. You can make this into basically something that has a single voltage supply and a single Thevenin's resistance. This is actually known as the output impedance or output resistance. Okay, so just so I can write these words down: resistance, right, which is what this R stuff is. I'm going to start kind of equating these two words, impedance. Okay, just so that we're not confused about it. Resistance is used when you're dealing with resistors, and this is very useful for direct current circuit. Impedance is basically a generalized version of resistance, but this works for AC circuits because what happens is that when we start adding capacitors or inductors into our circuit, these don't have resistance as a definition, but they do have impedance instead. So no resistance, but they have impedance. So impedance is just a more generalized version of resistance. Okay, so as I mentioned, right, I can simplify this, crazy circuit into something that just has one battery source and one resistance, and these are called Thevenin's voltage and Thevenin's resistance. And so the thing is like, what is this? I mean, how do I figure out what this is? Okay, so I'm going to do this. I'm going to show you how to do this with the voltage divider thing we already did from the previous section. But I'm going to put in some values. So you have a voltage divider, you have voltage source, you have resistor 1, resistor 2, and these could be different values. Okay, and what I'm going to do is I'm going to make voltage, the input voltage 9 volts. The resistor 1 here, 1 kilo ohm. In fact, I'll just write it up here, 1,000 ohms. Okay, and then down here, the resistor 2 is going to be 2 kilo ohms. Okay, right. And if you actually just, did the voltage divider equation, right? So voltage divider equation is Vn equals to R2, sorry, V out equals to Vn times R2 divided by R2 plus R1. So in this case, this is 9 volt. R2 is 2000. R2 plus R1 is 1000 plus 2000, so that's 3000. So this is actually going to be 6 volt. That's going to be the V out. Make this a little thinner. Okay. Okay. So we kind of already know what this V out is, but what we want to do is basically make this so that instead of having Vn and 2 resistor, we're going to reduce it by 1 component. Okay, we're going to make it into V Thevenin. Oops, make this circuit behave as if it's just V Thevenin and a single resistor, and basically your output is connected here instead. Okay, R Thevenin. Okay, how did the book like to draw this? Oh yeah, it likes to draw it like this. Okay, so this is this voltage across from top and bottom here is actually the V out. Okay. All right, so how do we do this? How do we make these things equivalent to each other? Okay, first of all, V Thevenin is V out when there's nothing connected to the output. So this is where a lot of students get confused because they're not used to, you know, dealing with circuit that has an output and input and stuff like that. They're just used to just dealing with a single circuit where you're not interfacing with something else. So this is the output of the circuit. Okay, we actually just calculated what the output of the circuit is, right? If nothing is connected to it. Okay, remember when the case where we connected this to a second voltage divider, it affected what this output is, right? In this case, we're gonna, in order to calculate what V Thevenin is, you just don't connect that to anything. So you can just treat this as if it's just a voltage divider that has no connection to it. So in this case, it's actually exactly 6 volts. Okay, done. Okay, 1 out of 2. What about R Thevenin? I'm going to redraw this circuit here actually. There's a little battery source. Oops. I should connect the resistor here, right? This is V out. This is R Thevenin. Okay, so we got that done. So now I have to figure out what this is. Okay, R Thevenin is found if you short the output and calculate I short. Okay, then you can use V Thevenin equals to R Thevenin times I short. So you solve this for R Thevenin, of course, which is V Thevenin divided by I short. And what the heck is I short? I short, right? If we go back to the original circuit, you have V in here, right? And you have V out. R2, this is R1. I short means you basically connect the output to ground. You can, in this case, you can just connect it like this, or another way to draw that is just to, you know, just have another ground here. These two grounds are basically connected to each other. Okay. So what does this do? Because we want to calculate I short circuit. So how much current, right? I short flows through the circuit now that it's shorted to ground. So the current only flows through R1 and not R2 anymore, because right now it has a path that directly goes to ground, right? So since there's some resistance here and there's 0 resistance on this wire here, right? All the current is going to flow through the short circuit instead, and no current goes through R2 anymore, right? It's just, the current will take the path of least resistance, and then with the least resistance 0, it's always going to go through that path instead. Okay, so this simplifies the circuit to make it look like this actually, right? R1. You know, there's some branch here that we don't care about because nothing flows through there, right? And then we have ground here, okay? And now we have a circuit that has a single voltage and a single resistance and a single current. And we can apply Ohm's law to calculate what this I short circuit is. I short circuit is just going to be Vn to ground, so that's going to be Vn minus 0 over R1. Okay, in other words, just Vn over R1. Okay, now we can plug this back in, right? Back over here. Let's do it nicely over the top here. Okay, so R Thevenin is V Thevenin, okay, which is actually 6 volts. Let's put 6 volts here. Okay, Vn is 9 volts. Okay, and then R1 is 1 kilo ohm. Okay, what is this equal to? It's going to be equal to 667 ohm instead. Okay, because this basically gives you a factor of 2/3, and then this, since it's the denominator, it actually goes to the numerator, so 2/3 of 1000 is 667. Okay, so that's R Thevenin. Okay, so that's the equivalent circuit. Let me so when you draw these equivalent diagram, so we should mark V Thevenin equals 6 volts. R Thevenin is actually 667. So we round up from 6. Oh, okay. And that's going to be equivalent to this particular voltage divider with these resistors. Okay, these are the same. These will behave exactly the same if the output is here instead. Okay, so you basically reduce the number of components from 2 resistors to 1 resistor. Of course, you can do this with more complicated circuit, then reduce everything, you know, from like 1,000 component down to 2, basically 1 voltage source and 1 resistor. There's actually an alternative way to calculate R Thevenin. The alternative way here is listed, you know, stated in the textbook. What you do is to replace all the EMFs, meaning all the voltage sources, right, with shorts, and then just calculate the equivalent resistance. What does he mean? What does the book mean by that? Okay, so in our circuit, right, we have this. Actually, in this case, I'm gonna draw it like this, like a battery, right? And there's a voltage divider on this side, R1, R2, like this. Okay, and this is V out. V out. Okay, how do I so replacing all the EMF with short circuit means you basically don't do this, and then you just connect the wire through this. Okay, so there's no EMF anymore. So now this circuit kind of looks like this. Okay, right, V out, R1, R2. So now instead of basically, you know, the current going through one resistor and then going through the other, since there's no EMF here anymore, no more battery here, right, the current can actually go kind of parallel to each other. So this is basically just equivalent to R1 parallel with R2, okay, which we can calculate, which is just 1 over R1 plus 1 over R2, all inverted. And then if you put in, this is 1K, this is 2K, common denominator between the two of them is 2K. So if you make this a 2K, then this numerator up here has to be a 2 also. Right now you have 3 over 2K, negative 1. So it's 2,000 divided by 3. And guess what that number is? 667 ohm. Okay. So we get the same answer for R Thevenin, no matter what. Okay. All right, so what I'm going to show you real quick is see how this is actually useful for that double voltage divider problem we had in the previous section. Okay, because previously you basically just had to do a bunch of circuit analysis in order to do this. What I'm going to do is I'm going to simplify this. Okay, since the circuit have same R's, okay, what's going to happen is that, right, instead of what I'm going to do is take this little piece here and make it into a Thevenin equivalent version. Okay, so this little piece here turns into just V Thevenin. Okay, R Thevenin. Okay, and this output here is going to connect to these two guys, right, which is still R and R. And then we're actually interested in what V out is over here. Okay, hopefully that makes sense what I did. I basically replaced these two resistors with a Thevenin equivalent 1 resistor, and then I have to replace this V in with the equivalent V Thevenin. Okay, and so those of you who did the homework already will know that this V out is actually going to be, if I remember right, V in over 5, not V in over 4 as you expected. Okay. Okay, so let's see if we can get the same answer here. Okay, so V Thevenin is the same thing, right, as this output here, right, where since we're dealing with just this part, right, this part is the output, right, this part where I'm circling here. Okay, that's just a 1/2 voltage divider. So V Thevenin in this case is actually 1/2 V in. R Thevenin, right, is equivalent. You can either do the I short circuit trick, or you can do the replace all the EMF with shorts and then make the resistors in parallel. But R Thevenin in this case is going to be 1/2 R instead. Okay. So if we go to this circuit, right, so this circuit is equivalent to 1/2 V in as an input, another the Thevenin resistance, which is 1/2 R. Okay, but then the rest of the circuit stays the same, R, R, and then we actually take V out here. Okay, we can do another Thevenin's equivalent here if we wanted to, but right, this is basically almost a voltage divider, except there's just 2 resistors there that are in series, right? So what this is equivalent to is the same thing as 1/2 V in, right? That's your input. Okay, and then this is 1/2 plus 1, because they're in series. This is actually 3/2 R. Okay, and down here is R, and then you have V out, so that's just a copy. And now this is just a simple voltage divider that you can apply. V out is going to be, well, it's not V in, it's 1/2 V in, because you started with 1/2. Okay, and this is going to be the bottom resistor divided by the bottom resistor plus the top resistor. Okay, this is the voltage divider equation as usual. Okay, if you solve this, you get 1/2 V in. All the R's actually cancel out. So 1 plus 3/2 is 5/2. And then since it's inverted, it's actually 2/5. Okay, and this will cancel out. And then you get exactly what you expect to be the answer. Oops, if I can write it down correctly. Okay. Which is exactly what you get in your homework if you did that already. Okay. So this Thevenin equivalent, right, allowed us to basically remove this weird parallel to ground thing and just make the whole thing a single current circuit, which is much easier to analyze because you can just add resistors in series very easily. Before we wrap up this chapter, I just want to, well, the book does it, so I'm going to do it too. Just to kind of emphasize how being able to analyze a circuit like this using this Thevenin's equivalent technique is going to allow us to basically connect different circuits together without having to worry about how they interfere with each other. Okay, so if I have some complicated circuit, with thousands of stuff in it, blah 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 blah, as long as I know there's some input to it, Vn, okay, and then we have some output to it, right? I can basically make this into a Thevenin's equivalent, right? The V Thevenin will not be Vn. I think most likely will not be. And then R Thevenin is basically kind of like the combination of all the resistance inside your circuit, inside all the different components in your circuit, right? And then V out, in this case, right, it's just going to be the output that you get. So one thing you can do by doing this is that, well, if I know what the input has to be, what the equivalent resistance or impedance in the case of AC circuit, and then the output of my thing, I can actually connect this to any device and know how this device will actually behave. Okay, and this is how people actually connect different devices together. So for example, when you connect your power charger, let's see in the camera, right? Your power charger from your into your laptop, for example, right? This power charger actually has some voltage output, some voltage input, right? And some Thevenin's resistance to it in case of DC. This is actually an AC-DC converter, so it's a little bit more complicated. But the DC side, right, will have some equivalent resistance on the output, and this is actually known as the output impedance of your circuit. Okay, that's why I start mixing up these impedance and resistance. People don't say output resistance because impedance is just a more general way to say the same thing. So that's why people always say output impedance. And then when you connect the end of this to your laptop itself has a input impedance to it. Okay, basically the output impedance of your power supply, this is going to be your Thevenin equivalent. Okay, you notice that. So there's some voltage supply here. That's the V Thevenin. This is equivalent to this here, right? And then we're connecting the output to some device, and this device happens to have some input resistance, input impedance of R load. Okay, this is going to be the input impedance. And I'm going to try to show you guys more of this in the lab. That way it's more solid as opposed to just speaking about this in theory. Because a lot of times what happens is then, if I try to define things too much just on paper, it is much harder to understand and actually more confusing than just me pointing at stuff in the lab. Okay, so the cool thing about this is that, right, once you have this, your circuit basically simplified to just one voltage, one resistance, and one output, right, you can connect this to something else, and that something else, as long as you know what the input impedance is, you're going to know exactly how it behaves, because now it's just a single voltage supply with one resistor here, right? And that's exactly what your voltage divider is going to be, right? So we can equate this to be R supply, right? And this is your V out, R load, right? And then you can always apply V out is going to be V supply, right, times R load divided plus the sum of the other two together, R load. Okay, which is really neat. Okay. Example of this, so I actually will talk about some examples on paper, but I will point them to you also in the lab. Okay, it's your USB-C. So you have for the non-Apple users, you have these USB-C cables, right? The universal serial bus. Okay, so if you're charging something, and there's different USB-C chargers. Some of them provide 3 amps of power of current. Some provide 5 amps. Some provide 1.5. But let's say you have a 3 amp. The standard for if you were to manufacture one of these USB-C 3 amp charger, which can provide up to 60 watts of charging, your Thevenin's equivalent resistance has to be between 100 to 200 milliohm. Okay, so 0.1 ohm to 0.2 ohm. And that's the standard that the USB people determine, so that whenever you plug something in, your device actually detects this output impedance from your power supply and knows, okay, I can draw 3 amps of power from it. Okay, and then your input side, basically, so this is sort of, so I kind of make a big mess here, right? Right, this is basically equivalent to the left-hand side of this stuff. The right-hand side is actually what you're powering, right? It's the load, which is what your charger is actually charging. So this is the USB-C power delivery port. So if your USB-C port has a little electricity bolt to it, that means it's a power delivery port. And that has a standard of 10 kilo ohms. Okay. It's interesting that, right, this is a very small resistance, this is a very big resistance. And if you were to apply this voltage divider equation to it, what happened is that you get a V out of basically 20 volts, 19.9999. Okay, you get slightly smaller because the power supply voltage for USB-C is 20 volts. You get slightly smaller, okay, like 1 in 20,000, right? So that's a very small difference, which your battery will be able to handle. So one cool thing is that when you're building a circuit or you're designing a circuit, what you want is actually you want your circuit to have a low output impedance, but you want the circuit that you're connecting to have a high input impedance. Okay, and we're going to see this in the lab when we deal with oscilloscope probe, which has a very high input impedance, and then your function generator will have a very low output impedance. Okay. One thing that's sort of neat also, if you were dealing with trying to send a signal from one place to another, or sending power from one place to another, you actually want to match the impedance. You want the input impedance and output impedance to be exactly the same. And that's due to this equation that the book derives for us. Because if you start off with power, remember power is equals to I times V, right? But if you can have the voltage divided by the resistors version of it, right? And this is the power that's being supplied from this side onto whatever you're loading here. Okay. Well, V out here, oops, so we'll do that. Okay, V out here, right, just follows the voltage divider equation, right, which is just V supply square times R load over, well, there used to be an R load square here, and you already have an R load here. That's why one of the factor cancels out. Okay. So this is the power that's going to be delivered to the load. And if you want to maximize something from your calculus class, right? If you want to maximize something, that means, well, you take a derivative of it and you find the zero. So that would either be a maximum or a minimum. Okay. So if you were to replace all these variables with just some general A, B square, the V supplied actually doesn't matter because that's not going to be one of the variables. Okay. And if you want to maximize this, you take this derivative turns out to be this complicated function. And if you solve this equation and you want it to be 0, okay, you're forced to have A and B to be exactly the same as each other. Okay, in this case, A is actually the load, B is actually the supply impedance. So in the case of wanting maximum power delivery between two different devices, you actually want impedance to be matched between them. An example of this are the BNC cables, which connect to our devices. These are little cables that you'll see in the lab. You connect to it, and then it'll connect to your your function generator. I'm just trying to draw a picture of it. The little port here. Now this little port, it'll say 50 ohm, and these cables, okay, are going to be made to be 50 ohm also, and therefore you have an impedance matching, and therefore you're maximizing the power delivered from your function generator into your cable. Okay, impedance matching also prevent this effect called ringing. This effect is caused by the difference in impedance. You can actually physically see it in your General Physics 1 class. What happens is that if you connect two ropes together, one thin one, one thick one, when you propagate a wave through it, what happens is that at this interface, some of the waves actually gets reflected back. And this is actually, you can actually really see this in your circuit if you were to build a circuit that doesn't have impedance matching, and you will actually see this ringing effect, which is this little oscillation here that you can see on this oscilloscope trace. And we can actually play around with this in the lab and you actually see it. Okay, so the next section, let's see how many minutes have I talked already. Well, okay, I'm just going to quickly kind of talk through the next section, 1.5. So, but I'm not going to assign any problem or have you guys do anything with it. So, but I think it is important for you to kind of hear through why this next section is useful if you were, building like a circuit solver yourself or something like that. Okay, so this is the matrix solutions to the resistor networks. So in all these resistor networks, right, you have a bunch of resistors, you have maybe something complicated like this, you have a bunch of resistors around, and then you have different batteries around, right? Maybe there's another battery here, right? And then you're trying to figure out what V out is, right? Right, stuff like that. And all of these, what you find is that you're going to end up with n number of equations by applying Kirchhoff's loop rule. Okay, and you're going to have n number of unknowns. So meaning, oh, what's the current going through this resistor, current going through, current go through here. Okay, and what that allows you to do is basically set up a system of equation that you can solve with just a matrix algebra. This matrix algebra is not simple, especially by hand. Okay, and the idea is that, well, now that you have all these equations here, so this is an example with just two equations and two unknowns. So this may be a circuit with just two objects in it, because what you end up writing using your Kirchhoff's loop rule, you have like this equation here, you get this equation here, but this can be reformulated into a matrix. And when you reformulate it into a matrix, what you can do is actually you just invert this matrix, find the inverse of this matrix, and then basically you have the solution to your problem. This is much less intuitive, but it's very useful if you were writing some code to write a circuit solver. And this is how a lot of circuits analysis software actually makes calculate their solutions. Okay, they don't do a substitution by hand like you would do in the homework problem here. Okay, and what's cool about this is that I didn't realize this at the time before I read this book. By going through this matrix solution, this scheme actually allows you to prove the Thevenin's equivalent theorem, which I have never seen proven before now. It's 2 pages of algebra. So if you do want to read through that, feel free to do so. It's a little difficult to understand because instead of resistance, he does this thing where he flips things around to do conductance instead. Okay, so, but we're not going to cover any of this. I just want you to have some conceptual background of why solving circuits with matrices can be useful. But since what we're going to end up doing was going to be simplifying a lot of our circuits down until it's just one voltage supply, one Thevenin's equivalent supply, and then one input low input impedance on the other side. Okay, so the last thing I'll just quickly chat about is the Norton's theorem. So Norton's theorem basically is the same thing as Thevenin's theorem, but the difference is that it's designed for constant current supply as opposed to constant voltage supply. So in our class, we are going to only use constant voltage supply, but there are circuits that have useful things if you can keep the current to be constant. In fact, in your voltage supply that you actually have in the lab, you can actually have a constant current instead of a constant voltage. But for all the stuff we're doing, we're going to have constant voltage instead of constant current. But to derive the Norton's equivalent is very similar. You have 2 rules where you find the short circuit and then you figure out what the output load is with no load, output voltages with no load. There's actually also an alternative rule, just like in the Thevenin's equivalent. I'm not going to assign any problem, but just know, if you ever have to figure out what the Norton's equivalent of a circuit is, you can just follow these rules and find it. Okay, so that's it for this chapter. So we'll see how the homework goes, and see you in the next chapter.